Okay, still loud, sorry. Okay, welcome to our next lecture in KDD. Last week we talked about OLAP, we started talking about OLAP. Before we continue to talk about OLAP, very important notification, please register for the exam. Already 200 of you have done that, but there's still 300 to go, according to the student course, not to this audience here, but just as a reminder. If you're not registered for the exam, you will not be able to take part in the exam. And we will not register you after the deadline has passed. Very important. Well, are there any questions regarding last week's OLAP lecture? Okay. Then we will continue to talk about OLAP, and today we will talk about the multidimensional ways of OLAP. Because last week I already introduced a concept called data cube. I not introduced it, but I used it. Today we will talk about what is multidimensional in OLAP. To note, a very important fact is that a data warehouse is always multidimensional. Often a multidimensional thing, the best multidimensional thing we can still visualize is a cube. We can't visualize a hexaeder, for example, very good, but a cube is something we can still visualize. And that's why we often talk about a data cube. Of course, a data warehouse is not only three-dimensional in many cases, but multidimensional. So we have more than 3 dimensions. The data cube is still the name for this multidimensional data model. To differentiate, we have to talk about two different things in a data cube. We have to first talk about dimensions. Dimensions are informations that are used to filter data. For example, an information might be the date. You can use the date to filter just sales that occurred in 2025. You can use the date dimension to filter just sales that occurred in January 2025, and so on. Another filter dimension might be gender. You can just filter sales that have been done by a male customer. You can just filter sales that are done by a female customer. Dimensions typically can't be aggregated and won't be aggregated. It's not important to aggregate them. While information that we want to aggregate, those things are called facts. For example, in a sales database, data warehouse, prices might be something we want to aggregate. We might want to aggregate all the sales, sum up all the sales we have done in a certain period of time, for example. And those two things are important to distinguish. But let's first take a look at a three-dimensional data cube. Let's say we have 3 dimensions in this case, because a cube is always 3-dimensional, and that's the last thing we can still visualize pretty good. Let's work with 3 dimensions in this case. We have 1 dimension, time. As I said, we might want to filter according to time. Another good dimension, often used dimension, might be region. Where did the sale occur? So did I make my sale in Nuremberg? Did I make my sale in Erlangen? Did I make my sale in Germany? Did I do it in Japan? Whatever. And the last dimension we are using is product category. So let's say we have dishwashers, we have washing machines, we have TVs, and all these things can be distinguished in the product dimension. One sale would be a little dot somewhere in this coordinate system. So a sale that occurred in Erlangen on the 1st of May 2023, and it was a washing machine, a Series 8 washer, might be located here. And a sale that occurred in Rome on the 6th of June 2024 with an iPhone. I'm not using an iPhone here for certain reasons. Might be located here. Those are simple single sales. The most granular sale that can occur. Of course, we are storing some facts with these sales as well. In this case, the price, we have a sale, the price we used to do this sale. So 1,250 euros for the iPhone and 430 euros for the washing machine. These are single facts. So the prices are facts. Now we can, think about even more dots being in here. Those are not only two sales we really have. We have a lot more than these sales. And those are dotted around the coordinate system at any place. Even more than we're showing here. A data cube only makes sense if we have millions of data points. Then we can put all the sales into a data cube, which spans around every single data point. We can then divide this big data cube into smaller cubes. For example, we can divide through countries in the regions. We can divide through years and product categories. And every single dot, which was in the bigger data cube, is also somewhere in a smaller cube. We can use these smaller cubes to analyze events separately. For example, we can now aggregate all the sales that occurred in Germany in 2025 for the TV category. And only the dots that are, the data points that are within the smaller cube would be taken into account for this aggregation. We can even divide our data cube into even smaller cubicles by dividing through quartils. Here. We can smoothly switch between granularities in each dimension, if there are granularities in a dimension. In this case, we might have a lot of granularities per dimension. That's something we will see in one of the next slides. Of course, there are also dimensions where we do not have granularity, male and female, for example, in a traditional sense. By dividing it into smaller cubicles, into finer granularities, we can do even more precise analysis. To really display the different granularities we have at hand in a multidimensional data cube, we can use the so-called multidimensional entity relationship model. For the ones of you who already know about the entity relationship model, this is not really the same to an ER model, but it's something that is very often used. In a multidimensional entity relationship model, we first give our database, our data warehouse, a name. In this case, the name would be sales. Then we display all the facts we want to store. So in this case, the only thing we want to be able to aggregate would be the price, so we only list the price. This is done in a really cube-shaped element of a model. And then we get to the dimensions. And dimensions can have different granularities. The granularities are shown from right, the finest granularity, to left, the coarsest granularity. So in our dimension time, the dimension we previously had, we have the finest granularity day. Of course, there might also be hour, there might also be minute, but in our case, we start at day as the finest granularity. After that, we might have month, but we can also go to week. So there are two parallel coarser granularities. Why? Well, a week can span several months. So calendar week, the next calendar week might also span May and June. So we have to put them in parallel because there's no certain distinction between these two. Then the next coarser granularity would be quarter, and then year. And by going from a coarser granularity to a finer granularity, we can split the data cube into finer, smaller cubes. We do the same thing for every dimension we have at hand. In this case, we have 3 dimensions: time, region, product, but there might also be more. So we can also have 15 dimensions. This MER model is pretty good in displaying these things. Are there any questions how to read an MER model? Okay. We can, in a data cube, go into finer granularities. We can also go into coarser granularities. If we are going from weeks to years, we aggregate more things. The whole narrowing the cube down and putting it into a coarser granularity can be also displayed as so-called cuboids. We have a basically n-dimensional base cube, and we can go to coarser granularities by merging different dimensions together. Well, not merging them together, but giving a selection or making a selection on different granularities. So for example, if we say we want all data, that's the 0D cuboid. If we either do a selection on time, item, location, supplier, so we have a 4-dimensional data warehouse in this case, then we are in the so-called 1D cuboid. So if we say we only select, we want only to analyze years, 2025, data of 2025, then we are in a 1D cuboid. If we then say we want only to analyze data from 2025 with TVs in mind, then we are in a 2D cuboid because we are selecting 2 dimensions. And we can go to the most dimensional cuboid, highest dimensional cuboid, if we select all dimensions. That's another visualization. It's called a lattice of cuboids. That's something you might read about, so it's important to note. Even more important for me as a data warehouse researcher is how to model a data warehouse. Because, well, we talked about having multiple dimensions. We can visualize that thing, but how do we put that into a database system? how can we get the concept, the model from our multidimensional entity relationship model into a real database system where we can only use relations. Well, there are basically 3 different concepts to do that. There's one, the star schema. In the star schema, we create a table, a relation for the fact table. So all the facts are put into one single table in the database system. And then we do one relation per dimension, regardless of how many granularities these dimensions have. So there would be one table for the dimension time, even if it has 4 granularities. We will see that in a visualization on the next slide. Then we can have the snowflake schema. The snowflake schema is basically the star schema, but we create one relation per granularity step. So we create for the time dimension we create not only one table, but we create 5 tables because we had 5 different granularities in the MER model. And basically, in database terms, the snowflake schema is a normalized version of the star schema. There are the so-called normal forms in database warehouse design or database design in general. And if you normalize a star schema to the 4th normal form, you will end up with a snowflake schema. But that's something about a database lecture. That's something Professor Lenz can do. And I will not teach you that. It's just a little side note. And then we can also have so-called fact constellations, where we not only have one fact table, but we have multiple fact tables, and we are reusing different dimensions. So we can do that with a star schema, we can do that with a snowflake schema. Most often it's done with a star schema, and we just share the tables that are for the dimensions. Let's do some examples because it's easier to comprehend with some examples. An example for a star schema would be this, where we have one central fact table with all the measures in here, so the data we want to aggregate. So in this case, we have unit sold, dollar sold, average sales as facts we can aggregate. And then we have 4 dimensions: time, branch, item, location. Those are the dimensions. And for example, the time table has a day of a week, month, quarter, and a year as different granularities. And all these granularities are stored in the same table. So we only need one foreign key to link to this single table. That's a star schema. Compared to that, and that's not a perfect snowflake schema, I have to admit, because we do not have enough place for that, because time would have to be normalized as well, branch would have to be normalized as well. It's just, something to point out how it might look like. We will have dimensions that are split into their granularities per table. Very important, this is not really a snowflake schema because it's not normalized perfectly. We would have to have 5 tables for time, 2 tables for branch, 4 tables for item, 5 tables for item, 4 plus 1, and we would have to have 5 tables for location, 2 plus 3. Why is this one thing called star schema, and the other thing is called snowflake schema. Well, it's pretty simple to think about that. Let's say in the star schema, we have one central fact table, and we have one table per dimension. If we draw that like this, it somewhat looks like a star. Not a perfect star, I'm not good in drawing, but it looks like a star. If we are talking about a snowflake schema, and let's use this imperfect snowflake schema and do it perfectly. So we have one table for day. We have one table for day of week. We have one table for month. We have one table for quarter. We have one table for year. We have in item, we have one table for item name. We have one table for brand. We have one table for type. And brand and type might be parallel, because brand and table are something you might, brand and type. We have Samsung producing TVs, we have LG producing TVs, so those are overlapping, so those are in parallel. And we have one supplier, which might be together again, merging that together. Then we have branch name and of course a granularity branch type. In location, we have street, we have city, we have province, we have country. This, if we even would split more and extend more, somewhat looks like a snowflake after some time, with some imagination, of course. And that's the reason why these schemas are called star schema and snowflake schema. One thing we can often ask in an exam to ask you whether you understood the principles of a star schema and a snowflake schema would be to give you an MER table and ask you how many relations, how many tables do we need to put that into a database system if we would do it as a perfect star schema. First question, think about how many tables do we need to put this MER table into a perfect star schema. So a star schema according to definition. I will give you 1 minute and then I will count up from 1 towards 10, let's say, and you simply raise your hand once I get to the number you think is correct. Remember, a star schema has one table for the fact table and one table per dimension. So it's not really a very hard calculation. Okay, I will count up and you simply raise your hand at a number you think is correct. Please raise your hand even if you're not sure. I just want to see how many people of you understood the principle and how many didn't. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, only one person is awake. That's not that great, but your answer was correct. So we have 4 tables in this case. Why do we need 4 tables? Because we need one table for the fact table. This is the right-hand thing here. This table would include the price, and it would include foreign keys to the 3 tables displaying the 3 dimensions we have at hand here. We have 1 dimension time, we have 1 dimension region, and we have 1 dimension product. So we have 4 tables at hand for star schema. Is that something, even if you didn't raise your hand right now, you can understand why we need 4 tables? Again, that's a question I might ask for in the exam. And it's a pretty easy question once you understood the principle. So it's pretty safe points and pretty quick points. Are there any questions? Okay. Then the next question is, if we not do a star schema, but a snowflake schema, where we not only have one table per dimension, but we have 1 table per granularity step. And we are talking about an ideal snowflake schema. How many tables do we need in that case? Again, think about it. It's a little bit harder. It will be a little bit higher number. So if you end up at 3, you're wrong. But it's pretty easy. You just have to count. I give you again 10, 20 seconds, and then I will count up again. How many tables do we need if we do a snowflake schema instead of a star schema? Okay. Let's start at 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, there was one risen hand at 10. There was the most hands at 11 and some hands at 12 and 13. Let's count. Well, we still need a table for the fact table. 1. Then we need 1 table per granularity step. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11, with the most risen hands, was the correct answer. So if I ask you for star schema, in this case, it's 4, and a snowflake schema, a perfect snowflake schema, would be 11 in this case. Pretty easy to do, and that's something I often do in the exam. So pretty easy answer if you understood the principle. Well, then there's another case, the fact constellation. This thing, again, most often is based on a star schema. So we only have 1 table per dimension, both a time, branch, item, and location. But we are reusing those dimensions in different fact tables. For example, we can have a shipping fact table, and we can have a sales fact table. And of course, both the shipping fact table and the sales fact table can use the same locational table. Of course, a location is something that is the same for both cases. We will have streets, we have cities, we will have provinces, we will have countries. That's pretty easy to do. Yeah, fact constellation. Can also be used in a snowflake schema. Then it gets a lot more complex, so we will skip that. The next thing we have to talk about is the facts, the measures. We already said that we can aggregate these facts. Aggregation is something we didn't yet talk about in detail in KDD. In data cubes or in data warehouses, we divide measures or aggregation functions into different categories, and we have two different scales or different categorizations for measures. First, let's say what is a measure. A measure can either be a single fact, or it can be a data cube measure, which is a aggregation function used in a data cube to evaluate different things in there. The first categorization we want to talk about is the categorization between distributive, algebraic, and holistic measures. If we have a distributive measure, data cube measure, we can derive this the result by applying the function to n aggregate values obtained for n partitions of the data set. And that should be the same as if we're deriving the function to apply the data, the function to all the data. So basically, if we are taking a look at this is the whole data set, okay? We have certain points. And the results of distributive data cube measures should be the same if we first apply, for example, count to the first partition, 3, and then to the second partition, 2, and then to the combination of both, ends up at 5. And that's the same result as if we wouldn't have these partitions at all in the beginning and simply counted, would be 5. So count is a distributive function. We can do that around different partitions and end up with the same result. This is true, for example, for count, but it's also true for sum, it's also true for min-max. Those are good examples. Then we can have algebraic data cube measures, where we have some specific argument we have to use, so we can still use work distributive. For example, average. We can, of course, calculate the average of these 3 points and the average of these 2 points. Let's say the average of these 3 points would be 3 and the average of these 2 points would be 4. We can simply use these two and calculate the average between 3 and 4 and end up with a total average. That's something that isn't possible. 3.5 is not the correct answer for the total average. But if we use an argument to say, hey, we have 3 times 3 and 2 times 2, and then we use that to sum that up and divide it through 5, we end up at the correct average for all. So we can put in a certain additional argument to still work distributive. Is that obvious to understand? That's the definition for an algebraic data cube measure. You had a question? Okay. So that's something we can do. And then we have the last kind, where we can do distributive things, the holistic thing, where we have to take a look at all the data at hand. For example, a mode. There's no point, no way to find out what the mode of these 2 partitions would be in total if you simply know this is 3 and this is 4. Because how should we know how often a value occurs in total? That's not possible. So mode would be an example for a holistic thing. Same for median. There's no way to find that out. These three categories are very important to understand how we can work with the data warehouse, because the data warehouse gets big very fast, and it might also be distributed. Might be distributed amongst many servers. And then we have to work in different ways according to these kind of categories of a data cube measure to aggregate the facts. Another type of categorization of the aggregate functions of the data cube measures is the aggregation type. And that's more about the facts themselves. Not about the aggregate functions, but about how these facts are structured. There are again three different kinds of facts we can have. One thing might be a stock measure, a stock fact entry. This stock measurement was measured at a specific point in time and can be aggregated as you want. You can apply any aggregate function to this thing. For example, we can have a sales turnover. So how many items are ordered per day? If we know how many items are ordered per day, we can apply a count to that. We can simply count up how many items have been sold per year by adding up every single sales turnover per day. We can also apply a minimum and maximum. We can also apply a mode. How many sales do we have, not on average, but most often per day? We can apply a mean. That's something that happens to many different facts, and it's the best thing that can happen, because we can do many things with these facts. Then we can have a flow, where we have a measure over a period of time, where we can't do any temporal aggregation. But we can do every aggregation type. For example, if we are talking about inventory. So we know that on the 21st of June, we had 200 iPhones at stock. And on 22nd of June, we had 205 iPhones at stock. We can simply say, well, in total, we had 405 iPhones at stock. That's not possible, because we do not know how many are sold in this case, how many are re-added into the inventory. That's something that isn't possible to be aggregated over time. And then we have the last kind, the value per unit kind, where we can't sum at all, not only temporal, but we can't sum at all. For example, a tax rate. Tax rate is a good example. If we have, for example, a VAT tax applied to electronic devices of 19%, and a VAT tax of 7% for take out things in a delivery shop. We can simply say, our total VAT tax rate was 26%, because that's not how things are working. So tax rates are not to be summed and therefore are value per unit. Or also unit prices. We can say, because an iPhone costs 1,200 euros and a football costs 5 euros, in total our products cost 1,205 euros, because we do not know how many of these are sold in each case. And that's another distinction, more on the type of fact side. You always have to know what can I do with my fact. Of course, there are some aggregation functions we can always apply, minimum, maximum, average of things we can always apply, regardless of being stock, flow, or value per unit. Okay, any questions regarding this? Okay. Then we get to the last big thing. What can we do with DataCube? And we have to talk about basically 5 different operations we can do with a DataCube. We can have a slice and dice, we can have a roll up, we can have a drill down, and we can have a pivot. There are also things like drill across and drill through, but I will not get into detail on them. Drill across is about merging together different data cubes over different facts, and a drill through is going to the lowest level to get to the original data points. For the other operations, we can take a look at certain examples. The first operation we have to talk about is the slice operation. The slice operation is pretty easy to comprehend if you take visualize again a 3D data warehouse. If you would simply select all data points that occurred in Q2 of 2025 and analyzed all the data points that are in this slide, then you would perform a slide. So in a SQL query, you would say, select, let's do it in here, on here. Select maybe count of all things to have some aggregation. From, let's say we have a star schema at hand. So we have one dimension, one relation per time. So we have a fact table. We have the time table. We have the region table. And we have the category or product dimension. These have to be joined together, of course. That's something I will not write down right now because it would take too long time. And then I would say, hey, I just want where time, year equals 2025 and time quarter equals Q2. And that's a case where I only select one dimension, or do a subset selection of one dimension. That's done. That's called a slice, because it basically slices a whole layer out of the original data cube. So this operation here would be the slice. I can do the same thing for multiple dimensions. If I select, or if I basically select a subset of more than one dimension, so in this case, I would even not only say 2025 in Q2, but also say, hey, let's go to region, country, Germany, or country Italy. This wouldn't be called a slice anymore, but this would be called a dice. Since I basically do not select a whole layer, but I select basically a dice, a smaller dice. So this process in here would be called a dice. That's basically a subset selection. The two options we have at subset selection. We're calling it a slice as long as we only select one subset of one dimension, but as soon as we select more, if we narrow down more than one dimension, then we are doing a dice. We can also talk about switching between coarser and finer granularities. Those things are called roll-up if we are switching to a coarser granularity. So we are taking a look at a finer granularity, and then we are taking a look at a coarser granularity. That's called a roll-up. And the other way around, from a coarser granularity to a finer granularity, it's called a drill down. How can we do that in a SQL query? Well, we can always group by. If we would group by, for example, the time point here in first place, and then we would say, well, that's not fine enough. We want to take a look at, say, quartal instead. Then the process of switching from time from a group per year to a group per quartal would be called a drill down, because we are switching from a coarser granularity to a finer granularity. If we do the other way around, so we delete this group by, then we are doing a roll-up. Logic? Cool. I see some confused faces. I can't teach you all of SQL in here. That's something that has to be done in, for example, Einführung in Datenbanksystem by Professor Lenz. But maybe I just do that for the guys in here and girls in here that have some SQL experience, of course. I will not ask you to write a query. Maybe I will give you a SQL query and ask you which is an operation, but I do that rarely. That's not a usual question. And then the last thing, that's something we can do in a SQL query, but it's harder to do. Because of that, I will not show it to you in here. We can also pivot a cube. Pivoting a cube is just about rotating the cube. So taking a look at other dimensions first. You might know a pivot function from Excel sheets. And the same thing can be done in SQL as well. But that's, not that, obvious to do. It's just about taking a look at other dimensions first. That's the easiest way to describe how it's done, or what is done. It's necessary sometimes, but there you have to have more SQL knowledge and more experience. So it's more about visualizing a pivot for you right now. Okay. Are there any questions regarding the OLAP operations? If not, let's go through data warehouse design and usage very quickly, because I want to get to frequent patterns, so we can start with the exercise on frequent patterns next week, at least. We can design a data warehouse in different ways. We can, for example, go top to down. So we select all the relevant information necessary for a database, and then we select how many dimensions we want to have and whatever, and then we select the data. We can have a data source view where we start at the data point and then build a data warehouse around that. We can have a data warehouse view where we specifically first take a look at the fact tables and dimensions and then go, and we can have a business guided view. So we start by taking a look at the requirements of the end user and then design the data warehouse. Those are different views. All of these are valid. Depends on what is your use case. You might have a different view on a data warehouse. Pretty simple to do. I will not ask deep questions on that in the exam. It's just for completion in here. Then the data warehouse design process can be done top down or bottom up. So we start with planning and design, and then we go down, put in the data, or we can do bottom up, where we do rapid prototypes and go up. Of course, we can do that in different ways, software engineering wise. We can do that in a waterfall model, where we simply start with analysis, then we go to execution, then we go in testing and completion. Or we can do a spiral model where we do something like Scrum and design our model rapidly. So basically, top down would be more likely with waterfall, while bottom up would be more likely with spiral model. Typically, we start in the data warehouse design where we first think about the reason, the use case we build the data warehouse around. A data warehouse, reminder from last week, is subject-oriented, so we have to have a subject for the data warehouse, and that can be derived from the business process. Then we select the grain of data, so how fine granular should be the single data points in our data cube. We can also start with pre-aggregated data in a data warehouse. So we can have data per day instead of single sales, for example. Save some space. Of course, you can do less analysis, less precise analysis with these data. Then we select the dimensions. So what dimensions do we want to use to select subsets of data? And then we choose measures or facts that populate the data set so we can aggregate them. That's typical, the typical process. Sometimes it's done in another way, but that's the most common case. Very important, data warehouse construction is not that easy, and you will not be able to create a data warehouse just from being here in KDD. This is just a quick overview about data warehouses. If you're interested in building data warehouses yourself, you should go into a specialized lecture, which, for example, Professor Lenz, of course, can do. In here. We can have some interlinkage between different data warehouses, data marts. We already described these two terms within a company where we can have a very high-level corporate data model that puts out different data marts for different engineers, different interest groups, which are of course based on an enterprise data warehouse. These data marts can also be distributed, and this combines into a multi-tier data warehouse. Basically that's just a few. If we would have more time, I would go into more detail, but for now, let's skip. The data warehouse and data mining is something we already talked about in some detail. Why do we talk about data warehouses in KDD? Well, because data warehouses are about online analytical processing, and in KDD we are doing online analytical processing, basically. We are most often not working on OLTP databases. We are most often working on OLAP databases. Because we have integrated, very consistent, so not so dirty data, and that's very good for us. There is a lot of information about data warehouses. We know a lot about how to clean these data sets, how to integrate these data sets. Why shouldn't we use pre-processed data for our data mining and efforts if we already have a huge knowledge base about doing things? Also, we have some pretty important functions like drilling, dicing, pivoting with SQL, which is often faster than if we do that with pandas, for example. There are specific frameworks that are reusing data warehouse techniques directly in Python, for example, Modin, but that's something for another case. And we also have a lot of data mining functions that are already present within data warehouses, which is pretty nice. If we are using some predefined functions, then we are not longer talking about online analytical processing, but we are talking about online analytical mining. It's a little distinction if we are using these pre-selected data mining functions. We already talked about the process of extract, transform, load, creating a data warehouse through this extract, transform, load process, which includes not only these 3 steps, but multiple more steps. We talked about that last week. Leading to data marts, of course, we are doing our online analysis most often on data marts. Sometimes, if there are no data marts available, also directly in the data warehouse. And that's basically about data warehousing. We talked about what is data warehousing. We talked about how the general model looks like, what modeling functions, MER, we can use to display our cases. We talked about how to implement that in a database system. modeling wise. We talked very quickly about how we can create a data warehouse process wise. Again, I will not ask that in detail in the exam, so no worries about that. And we finished up with some rounding up how we can use that as a data mining expert. That's the most important thing for you. We can use that to have preprocessed data. And that's pretty nice for us. Was that a question or just a frustrated thing? Okay. And that's basically what we are doing within this lecture. Of course, data warehousing is a topic by itself. We had one lecture specifically about data warehouses back when Professor Meyer-Wegner was still in the chair. This lecture doesn't exist anymore, but the lectures by Professor Lenz are still more in depth than KDD on that. So if you're interested in that, go into them. And hopefully, in the winter semester, we have a new professor. Hopefully, the person that might come brings up some new lectures, maybe something about data warehousing is in there as well. But I can promise that to you since it's not fixed yet. Okay, and I put in some more books in here, some more literature. If you're interested in that, you can take a look at that as well. Are there any more questions about this chapter? If not, I will quickly go to frequent patterns. Okay, then let's go to frequent patterns. The next big chapter, and I hopefully get through the first method in here in the next half an hour. So we are prepared for next week's exercises. I will try to do that in some speed. In frequent patterns, we will talk first about basic concepts. Those are pretty easy to comprehend, so hopefully we can get through them very easily. Then we will talk about scalable mining methods. So our first methods we will talk about in detail. Specifically, today I'm hoping to talk about a priori, one of the oldest methods in this domain. Next week, we will talk about a more sophisticated method, FP-Growth, and some other approaches. A priori and FP-Growth will be your first submission tasks as well. So you will have to implement a priori and you will have to implement FP-Growth by yourself in the submissions, starting in 2 weeks' time, if I'm correct, or 1.5 weeks' time. Then we talk about how to use these frequent item set mining methods to find association rules, and we talk about how to identify patterns that are interesting. And we end with a summary, of course. Okay, let's start with basic concepts. First, what is frequent pattern analysis? To understand that, we first have to understand what's a frequent pattern. A frequent pattern is a pattern, specifically a set of items, subsequences or substructures that occur frequently in a data set. Well, that is a pretty broad definition, but for example, a good example for that would be what items are often bought together. For example, are footballs and football shoes bought together very frequently? Or are beer and diapers bought often together? Or something that is also very often, and we can go to some examples on the next slide. You see these examples a lot in, for example, Amazon, frequently bought together products. You see that sometimes in in courses. This is an example from Coursera, for example, where you might also be interested in these courses. How's that done? Well, by taking a look at what others often did do after taking one course. They also took another course, and therefore it's a frequent pattern which we can recommend you as a user. And also with Netflix, Prime Video and Co, you also have customers also watched. What are customers often watching together? Those are frequent item sets. I have to go back to the previous slide. While it's pretty simple to understand the concept of frequent pattern, those are intrinsic and very interesting properties of a data set, because we can do a lot of things with these things. So we, in the first lecture, talked about what is data mining. Those have to be implicit actions within a data set to call it data mining. Frequent patterns are definitely data mining to identify frequent patterns. A very important note about the examples: frequent pattern analysis is often only the basis, the foundation of these recommendation systems. They are sometimes more complex than just frequent pattern analysis, but they are always the basis of these recommendation systems. Just a little disclaimer, so you don't know, just knowing about a priori is not enough to go to Amazon and say, hey, I can build your recommendation system. That's important note in here, so nobody is confused about that. But the foundations are important. Also, frequent pattern mining is very important for other functions. For example, we can do correlation analysis, we can do classification, we can do clustering, we can do different things based on frequent pattern mining. This is just a list, so you know where it's used. We can go over that. More important is, again, what terms are we using in frequent item set mining? And those terms are now very important. First, we have to define, if we are doing frequent pattern mining, the so-called term frequent item sets. To know about frequent item sets, we first have to define item sets. An item set is pretty easy to define. It's just a set of one or more items. So a K item set would contain K items in a set. An example for an item set might be beer and diapers. This would be a 2-item set containing the items beer and diapers. Important, it's a set, so it doesn't include duplicates. That would be a multi-set, but we are talking about a simple set. And the order within that set is not relevant. So it's not relevant whether diapers comes first or beer comes first. Those are both present. Those are the properties of a set. Based on an item set, we can define 2 different kinds of support. Support is the next important term. We can either have absolute support, also often called support count, which is basically the term how often does this specific item set occur in a bigger data set. Just how often. So if beer and diapers occur in our database 3 times, the absolute support would be 3. And then we can have the relative support, which is just in how much % of a database does this item set occur. So if beer and diapers again occur 3 times and we have 100 transactions in our database, the relative support would be 3% of that item set. And we define a frequent item set as frequent, we define an item set as a frequent item set if the support, either the absolute support or the relative support, is no less than a minimum support threshold, called min-sup, for minimum support. Let's take a look at an example. we have a transactional database where we have 5 transactions with a transaction ID 10, 20, 30, 40, 50, and some items stored in this transactional database. So in the first transaction, the customer bought beer, nuts, and diapers. This is also a set. This is also an item set. Beer, nuts, and diapers. The order is not important, and it's just about many items being bought together. In the second, we have beer, coffee, and diapers, and so on. And we set a minimum absolute support threshold in this example to 3. Then we can first take a look at the frequent 1 item sets. So frequent item set with a length 1, so containing only 1 item. To do that, we first have to count how often beer occurs. Beer occurs 1, 2, 3 times. So beer is certainly frequent. Also, nuts occurs in 3 transactions, diapers occurs in 4 transactions, eggs occurs in 3 transactions. So we have 4 frequent 1 item sets in this case. And we simply count how often that occurs. For the 2 item sets, we only have beer and diapers. Beer and diapers is part of transaction 10, transaction 20, and transaction 30. Again, order is not important, so it's not important whether it's beer and diapers directly or beer, nuts, and diapers. As long as beer and diapers are present in the same transaction, it counts as 1 occurrence. Okay? So beer and diapers occurs 3 times in total, and therefore we have a frequent 2 item set, beer and diapers. Since no combination of 3 items is present more than 3 times in our transactional database, we have non-3 item set that is frequent, non-4 item set that is frequent, and no 5 item set that is frequent. Something I would move to the next lecture due to time purposes are association rules. Please remember me to talk about association rules next lecture, because we do not need that for a priori, so we will skip it for now. We will talk about that next week, okay? Please remember me to do that. I will skip that in here. We will go back to that afterwards. What we need also not only is frequent item sets, we can also talk about closed item sets and max item sets, but that's something we also do not need for frequent for a priori, so I will also skip that to next week for time purposes. Please remember me to do that as well. We will do these examples with some time next week. I will now go to scalable frequent item set mining methods because I want to talk about a priori. To understand a priori, so how can I find these different frequent item sets of length 1, of length 2, of length 3, of length 4, we first have to understand the so-called downward closure principle or property. Since we know that beer and diapers is frequent in our little example we did previously, we of course always know that beer and diapers as a 1 item set also have to be frequent. And this is true for all frequent item sets. If we know that a 3 item set is frequent, then any subset of this 3 item set is automatically also above the threshold and therefore is also frequent. Because if we know that the combination beer, diapers, and nuts occurs often enough in our database, we know that beer and diapers is also often enough in the database. It might be present more often, but at least how often the bigger data set is. And this term can be used by a priori to do the so-called a priori pruning principle, because we can also talk about it the other way around. The a priori pruning principle is basically the other way around, that we know that if any item set is frequent, any superset, so any set containing more items additional to the original items, that this superset can be frequent. So if we know that in our example, diapers and nuts as a 2-item set occurred 2 times, we know that diapers, nuts, and any other item set, any other item can't be above 2. How should that happen? It's not possible if beer and nuts are only in 2 transactions together, that beer, nuts, and any other item can be in more transactions. That's not possible. And that is used by the a priori algorithm to be able to not test every possible combination, but only test likely combinations, and therefore speeding up the process of finding frequent item sets by not testing every combination, which would be the simple solution, but a costly solution to finding frequent item sets, to be faster. And a priori is basically working in a 3-step process. First, we scan the database once to find every frequent 1-item set. How is that done? Well, we take a look at the whole database, note down every item that occurs in any transaction, and in parallel count how often a single item is present in the database. After we have done that, we can prune every non-frequent 1-item set, so everything that is not above min support, and use the other, the leftover frequent item sets to generate candidates for length k item sets. Specifically, if we start with 1-item sets, we generate length 2 item sets. And we then only have to count our candidates, not every possible combination. And we do that as long as we can generate candidates. We will have a small example in a second that might be more obvious than this one. And after the point where we can't generate any more candidates, we stop the process and we found all frequent item sets. And it's guaranteed to find all frequent item sets. Let's do it in a small example. Let's start with a transactional database containing 4 transactions. And for simplicity, we have only items A, B, C, D, E in here, okay? Every letter is a single item in this case. We have the min support defined as 2 in this case. So the first step, according to our algorithm, is to scan the database once to get all frequent 1-item sets. So let's do that. Well, if we go around here, we have A as an entry. So we note down, we have A 1 time. When we note down, we have C 1 time, we have D 1 time. Go to the next transaction, we have, well, let me do that on the blackboard as well. So we have A 1 time, we have C 1 time, we have D1 time in the first transaction. Now we go to the second transaction, where we have B. Well, B is not on our list yet, so we simply create B, count it up by ones. We go to C. OC is already in our list, so we simply increase the count. We have E, which is not in our list yet, increase the count by 1. Go to the next transaction with the ID 30, A, B, C, E, increase A, increase B, increase C, increase E, and in the fourth transaction, we have B and E. So we have a total count of 2, 3, 1, 3, 3. So our frequent one item sets would be everything besides D. We can do that pretty easily. So basically, we count A, we count B, we count C, we count D, we count E, and then we prune everything that is not frequent. So in this case, D. That's the first step. Now we get to the first step of the iteration, where we generate candidates and only count the candidates. Candidates are, according to the a priori principle, only combinations of these items. So A and B is a candidate, because both of them are frequent. A and C is a candidate. A and E is a candidate, as well as B and C, B and E, and C and D. Those are the possible candidates we can generate by simply combining them into every possible combination. And now we simply have to go through the database again and count how often A and B is occurring, A and C is occurring, A and E is occurring, and so on. We can do that. You can do that as well. A and B is, for example, only in transaction 30. A and C is in transaction 10 and in transaction 30, and so on. By doing this pruning, we didn't have to count any combination with D. We didn't have to count them. And that's saving us some effort in a small database like here, but think about a big database with millions of different items. There it saves us a lot of effort, that we do not have to count smaller combinations. Basically, after counting, we do the same thing we have done with the one item sets. We are simply pruning the ones that are not present in our database. And now we get to a pretty important step. We get to a step of combining again. Very important. Think about what combinations, according to the a priori pruning principle, can we generate out of these things? Yeah? Okay, let's think about A, B, C. A, B, and C. We see that A, B, and C are all present somewhere in here. But to check whether this is a valid candidate, we have to check that A and B is frequent, A and C is frequent, and B and C is frequent. So all possible subsets have to be frequent. Let's take a look at this. A and C is frequent. So this is frequent. Oops, sorry. B and C is frequent, but A and B is not frequent. So it's not a validated candidate because this is not frequent, this can't be a candidate. The only candidate we can generate, if we go around that in this principle, is ACE. Because in this case, B and C as a subset is frequent, B and E is frequent, and C and D is frequent. So all possible subsets are frequent. So the only candidate we can really generate is B, C, and E. That's very important. Very important and something I often ask for in the exam. Again, just a little notification, because only if you understood that, you understood the a priori pruning principle. Every subset has to be frequent. If we count that, we end up with BCE at a count 2. So if we are pruning that, BCE is still frequent. And then if we do a new combination, we can't combine into any length 4 item sets. Therefore, the algorithm terminates. And we end up with A, B, C, E, AC, BC, BE, CE, and BCE as all of our frequent item sets we can find. And that's basically a priori. It's a little bit more complicated than just creating every possible combination of item sets and counting it, but it's a lot faster than creating every possible combination. There are some downsides to a priori, and I think we can get to them today, so we will do that. Very important, I already said that, if any subset of an item set you wish to generate is infrequent, then it's not a valid candidate. So basically this example in here, okay? That's very important, and basically the whole slide is about this. How do we generate candidates? Well, we combine everything together, and then we are pruning combinations that have infrequent subsets. That's the easiest way to get to that. There are some more sophisticated solutions to that, but you can use them, but you do not have to use them. A priori is more efficient than counting every possible combination, but it's still very inefficient. Why? Because we have to go over the original database multiple times. Specifically, we have to go over the original database k times, where k is the number of the highest candidate length. Pretty easy. So we have to scan the whole database a lot of times. If we're working on a production database, an OLTP database, this might put a lot of strain onto the database system. And even in an OLAP database, it's something you would want to avoid, because reading into a database, if it's not a in-memory database, is requiring you to read from the hard drive or the SSD, which is something you do not want to have. There are many improvements that have been proposed to do that. For example, there are improvements to reduce the passes of database scans by doing partitioning or dynamic item set counting, or to shrink the number of candidates by hashing. These 3 improvements we will talk about next week. We will also talk about a completely new method, which makes sure we only have 2 scans of the original database, namely FP growth. Those 2 things are something to do next week, and I'm pretty much exactly at the point I wanted to get to today, because now you have a priori, now you can do a priori by hand in the exercise, and that's something I hope you can do with the knowledge from today. Basically, that's what the exercise sheet is about. There is also FP Growth in there, but maybe I will reorganize the exercise sheets a little bit with the tutors to make sure you only talk about things you know about. Okay, are there any more questions about frequent patterns up to this point? It was a little bit speedy, but hopefully it was understandable nevertheless. If you have questions, visit the exercise, and of course you can always ask questions in the forum. One little note, since next week Monday is a holiday and Tuesday is a university holiday, so Tuesday no lectures and no exercises take part. If you are in a Monday or Tuesday exercise, please visit the Wednesday exercise. Oh, we do not have to reorganize then. Perfect, because the Wednesday exercise is after next week's lecture, so perfect. This week is also the week of Berg, so if you visiting Berg, have fun at Berg, do not drink too much, and see you next time, next week. Have a nice time. Bye.